In laboratories scattered across the world, something extraordinary is happening, and something extraordinary is failing. They call it the most powerful machine ever conceived, a quantum computer, a device that doesn't merely calculate, it explores all possible answers simultaneously, navigating the ghostly realm of superposition where particles exist in multiple states at once. With it, we might design medicines atom by atom, decode the protein folding that causes disease, model Earth's climate with perfect fidelity, unlock encryption that guards the world's secrets. But there is a problem. It breaks. It breaks with a whisper. To understand how profound this failure is, we must first grasp what makes quantum computers so remarkable. A classical computer, the one in your pocket, the one launching satellites, processes information as bits, ones and zeros, on or off. It evaluates possibilities one at a time, marching through calculations in sequence. A quantum computer does something the universe barely permits. It uses quantum bits, qubits, that can be 0, 1, or both simultaneously. Add a second qubit, and you have 4 states at once. 3 qubits, 8 states. 4, 16. By the time you reach just 300 qubits, you're processing more simultaneous states than there are atoms in the observable universe. This isn't faster computing. This is a different kind of thinking entirely. But here is what no one tells you in the glossy presentations and venture capital pitches. These quantum states last for microseconds, sometimes milliseconds if you're fortunate. Current state-of-the-art quantum computers have error rates between 1 in 100 and 1 in 1,000 operations. That means every few hundred calculations, the answer changes, unpredictably, irreversibly. Imagine trying to perform surgery while the patient's anatomy keeps rearranging itself. That is what it means to compute on the quantum. The enemy has a name: decoherence. Every quantum system exists in 2 worlds. There is the pristine mathematical world of perfect isolation, where qubits maintain their superposition. And there is our world, the thermal, vibrating, electromagnetic chaos of reality. The moment a qubit interacts with anything, a stray photon, a magnetic field fluctuation, the thermal jitter of nearby atoms, its quantum information begins to leak into the environment, like heat escaping through a poorly sealed window. Scientists have tried everything. They cool qubits to temperatures colder than deep space, just thousandths of a degree above absolute zero. They encase them in vacuum chambers, shield them with layers of metal, suspend them in magnetic traps floating in perfect isolation. Still, the quantum information dissolves. Every computation becomes a race against time. Finish the calculation before decoherence destroys your answer. And here is the truly bitter reality. As you add more qubits to solve harder problems, the errors multiply. Each new qubit is another point of failure, another opening for decoherence to destroy your work. By 2023, after decades of work and billions of dollars invested, the quantum computing industry faced an uncomfortable truth. We could build machines with dozens, even hundreds of qubits, but we couldn't make them reliable enough to solve problems that mattered. The promise was fading. The dream was dying in the noise. But in that darkest moment, a handful of physicists were pursuing a different vision. Not faster qubits, not colder temperatures, not better isolation. They were chasing something that sounded impossible. What if, they asked, we stopped trying to protect the qubit from the environment? What if we could encode information in a way that the environment simply couldn't see? To understand what they meant, we must leave the laboratory. We must travel to one of mathematics' most elegant territories, a place where coffee cups become donuts and shape matters more than size. Welcome to topology. Topology is the mathematics of properties that survive deformation. A coffee cup and a donut are topologically identical because both have exactly one hole. You could mold one into the other without tearing or gluing. But what does this have to do with quantum computing? Everything. Imagine encoding information not in the state of a particle, but in the pattern of how particles move around each other, in the geometry of their paths, in the topology of their braids. A small vibration might shake the particles slightly, but it won't change the fact that one particle looped around another. That topological relationship, that knot in spacetime, remains intact. This is the insight that changes everything. If you could encode quantum information in topology rather than in fragile quantum states, if you could store your data not in what particles are, but in how they braid, then you might build something the universe cannot break. In our ordinary three-dimensional world, particles come in two varieties. There are fermions, electrons, quarks, the matter that builds everything. And there are bosons, photons, the carriers of force. Swap two identical electrons, and the quantum mathematics demands they acquire a negative phase. Swap two photons, and nothing changes. This isn't arbitrary. It's woven into the fabric of three-dimensional space. But in 1977, two Norwegian physicists made a curious discovery. In a two-dimensional world, the mathematics doesn't demand this restriction. Think of particles as dancers moving on a stage. In 3 dimensions, if two dancers switch positions, you can always rotate the stage to make it look like they never moved at all. The topology of their exchange is trivial. But on a flat two-dimensional surface, something changes. If one particle circles completely around another, that path creates a topological feature, a winding number, that cannot be undone without cutting through the plane. The mathematics suggested particles in 2 dimensions could have any quantum phase when exchanged, not just the 2 options allowed in 3 dimensions. Any phase, any statistics. The physicist Frank Wilczek gave them a name, anyons, because they could be anything. For years, anyons remained mathematical curiosities. Beautiful ideas on paper, perhaps, but with no connection to reality. Then in 1982, physicists discovered something extraordinary about electrons trapped in 2-dimensional sheets. Take a layer of material just a few atoms thick, cool it to near absolute zero, apply an enormous magnetic field, tens of thousands of times Earth's magnetic field strength. At specific field values, the electrons begin to behave strangely. The electrical resistance doesn't vary smoothly. It jumps in discrete steps, forming plateaus of perfect quantization. This is the fractional quantum Hall effect, and it won a Nobel Prize. But buried in those measurements was something even stranger. The system was creating excitations, disturbances in the electron liquid that carried a fraction of an electron's charge. 1/3 of an electron, or 1/5. Impossible objects that only exist as collective behaviors of many electrons dancing together in their magnetic prison. These fractional excitations were quasi-particles, not true particles, but emergent behaviors of a complex system. Like the way ripples aren't water, but patterns in water. And they obeyed anyon statistics. In 2020, physicists measured them directly. They watched anyons braid, watched their quantum states change based purely on how they looped around each other. The mathematics of the impossible had become real. But the anyons in quantum Hall systems had a limitation. They were abelian anyons. Their braiding produced simple phase changes. Useful for some applications, but not powerful enough for universal quantum computation. For that, you needed something more exotic. In 1937, Ettore Majorana predicted a particle that was its own antiparticle. A fermion that, if it met itself, would simply persist. Not annihilate in a flash of energy, but continue existing. Majorana disappeared that same year, walking onto a ferry and never returning. For 7 decades, his particles remained equally elusive. Until physicists realized, you don't need to find Majorana particles in nature. You could create their quantum mechanical equivalents, Majorana zero modes, in specially engineered materials. The recipe sounds almost alchemical. Take a semiconductor nanowire, indium arsenide, just atoms wide. Place it next to a superconductor, aluminum, cooled until its electrons move without resistance. Add a magnetic field. Under these precise conditions, the material enters a new state of matter, not solid, liquid, or gas, not ordinary metal or superconductor, a topological superconductor. And at the ends of this wire, bound to its edges like mathematical ghosts, appear Majorana zero modes, half particles, exotic quasi-particles that only exist in pairs, separated in space. These are non-abelian anyons. Braid them, and they don't just acquire a phase, they fundamentally change which quantum state the system occupies. This is computational. This is universal. This is what makes topological quantum computing possible. For 2 decades, Microsoft Station Q, a laboratory in Santa Barbara led by Chetan Nayak, pursued this vision with quiet intensity. They were building something no one had built before. Not just individual Majorana zero modes, but networks of them. Arrays that could be braided, measured, controlled. On February 19, 2025, they revealed what they had been keeping hidden. Majorana 1, the world's first topological quantum processor. 8 qubits, not hundreds, not thousands, just 8. But these 8 qubits are different from any that came before. Each qubit is formed from multiple Majorana zero modes, braided together through a structure they call a tetron. 4 Majorana modes arranged in a specific geometry. Information is encoded not in where the modes are, but in the topology of how they're connected. The paper, published in Nature that day, contained measurements that had never been seen before. Interferometric readout of the quantum state, single-shot parity measurements, the smoking gun for topological qubits. We have created a new state of matter, Nayak told the gathered scientists. A topological superconductor, and we can control it. The qubits were small, fast, digitally controlled, and this was the revolution. They had error protection built into the hardware itself. To truly grasp why this changes everything, we must understand what topological protection actually means. Imagine you're trying to store a piece of information, a single bit, 0 or 1. In a classical computer, you might represent it with voltage. High voltage is 1, low voltage is 0. Noise can flip this bit. A voltage spike, a cosmic ray, thermal fluctuation. Suddenly, your 0 becomes a 1. In a conventional quantum computer, you encode information in the quantum state of a particle. Is it spin up or down? Is it in the ground state or excited state? But quantum states are exquisitely fragile. Any interaction with the environment causes decoherence. The state collapses, and your information is lost. Now consider the topological approach. You don't store information in any single mode. Instead, you distribute it across the collective state of all the Majorana modes. The information lives in whether certain pairs of modes are fermionically occupied or not, a global property of the system. To read whether the qubit is 0 or 1, you must measure the parity across distant modes. You must ask, has anything changed about their topological relationship? Local noise, a phonon, a stray magnetic field, thermal fluctuation, cannot change this answer. It might wiggle the modes, shift their energy slightly, but it cannot change whether two distant modes share an even or odd number of fermions without creating or destroying fermions, which is forbidden by conservation laws. The information is protected by the topology of quantum mechanics itself. It's as if you wrote a message not in ink that can fade, but in knots that would need to be cut to be changed. And in the quantum world, cutting requires energy that local noise simply doesn't have. The true power of topological qubits emerges when you consider scale. Current quantum computers require enormous overhead for error correction. To create one reliable, logical qubit, you might need dozens or even hundreds of physical qubits constantly measuring and correcting errors. This overhead is crushing. Google's breakthrough Willow chip has 105 qubits, but can only create a handful of error-corrected logical qubits from them. Microsoft's topological approach inverts this equation. The error protecting is intrinsic, built into the hardware, not added through software. Their quantum error correction codes reduce overhead by roughly 10-fold compared to conventional approaches. The roadmap they've published is audacious. From 8 qubits, they plan to scale to arrays of tetrons, building quantum processors with hundreds, then thousands of topological qubits. And ultimately, their architecture has a clear path to 1 million qubits on a single chip that could fit in your palm. 1 million qubits. That's not just a bigger quantum computer. That's the threshold where quantum computers stop being laboratory curiosities and become tools that can reshape civilization. Let us speak plainly about what 1 million qubits might accomplish. There are roughly 200,000 proteins in the human body. Each one folds into a specific three-dimensional shape, a shape that determines whether it heals or harms, whether it enables life or causes disease. We cannot predict most of these folds. Classical computers collapse under the exponential complexity. A protein with just 100 amino acids has more possible configurations than there are atoms in the universe. But folding is quantum mechanical. Electrons interacting, bonds forming and breaking. A system that exists in superposition until it finds its lowest energy configuration. A 1 million qubit quantum computer could simulate these processes exactly, not approximately, exactly. Watching in real time as chemistry unfolds according to quantum rules. Every drug we've never discovered, every disease we've never understood, every protein we've never been able to design, all suddenly within reach. Or consider materials. Somewhere in the vast space of possible atomic arrangements exists a room-temperature superconductor, a material that conducts electricity with zero resistance at everyday temperatures. Find it, and you revolutionize energy transmission. No more power lost to resistance in electrical grids, maglev trains that cost nothing to run, electronics that never heat up. Classical computers can't search this space. There are more possible atomic configurations than there are stars in the visible universe. But quantum computers can. They can simulate matter at the quantum level, exploring chemical space with the same efficiency that chemicals themselves explore it. Climate modeling. The Earth's climate is a quantum system. Molecular interactions, photon absorption, chemical reactions in the atmosphere and ocean. Our best supercomputers approximate these processes crudely, sacrificing accuracy for speed. The predictions we use to plan our civilization's future are educated guesses, averaged over uncertainties we cannot resolve. A quantum computer doesn't guess, it calculates. It tracks the quantum dance of molecules as they absorb heat, react, flow. It resolves the feedback loops we currently can only estimate. We might finally see with clarity what we're doing to our only home. And yes, there are darker possibilities. Encryption protecting the world's communications could become vulnerable. Financial systems could be optimized or manipulated at unprecedented scale. Weapons systems could be designed that we cannot yet imagine. Power of this magnitude is never neutral. It amplifies human intention, whatever that intention might be. But topology offers a curious gift here. The very properties that make topological qubits stable also make them slower at certain operations than conventional qubits. They're fault-tolerant, but not infinitely fast. This creates a window, perhaps a narrow one, for humanity to develop defensive strategies before quantum computing reaches its full power. Let us be clear. We are not there yet. The journey from 8 qubits to 1 million is not a straight line. The Majorana 1 chip is a proof of concept. It demonstrates that topological qubits can be created, measured, and controlled. But it cannot yet perform meaningful computations. Each tetron, the basic building block, requires extraordinarily precise fabrication. The indium arsenide nanowires must be grown with atomic perfection. The interface between semiconductor and superconductor must be pristine. The magnetic field must be tuned to millitesla precision. At Purdue University's Microsoft Quantum Lab, Tyler Lindemann spends months growing the semiconductor-superconductor structures. A single misplaced atom can destroy the topological behavior, he explains. We're building materials atom by atom, and we need every atom to be exactly where it belongs. Then there is the challenge of braiding itself. To perform quantum gates, Majorana modes must be moved around each other in specific patterns. This requires exquisite control over the quantum state while maintaining topological protection. The team has demonstrated single-qubit operations, but multi-qubit gates, the interactions between qubits that enable complex calculations, remain difficult. The braiding must happen faster than decoherence can intrude, yet slowly enough to maintain quantum coherence. And then there is measurement. To verify that computations are correct, you must read out the quantum state without destroying it. The interferometric techniques in the Nature paper show this is possible, but scaling these measurements to thousands of qubits will require engineering that hasn't been invented yet. Microsoft is not alone in this pursuit. The future of quantum computing has become too valuable for a single path. Google's approach uses superconducting qubits with heavy error correction. Their Willow chip achieved below-threshold error rates, meaning each additional qubit actually reduces errors rather than multiplying them, a fundamental milestone. IBM is building modular quantum systems, connecting multiple processors to reach thousands of qubits. Their roadmap calls for 100,000 qubits by the end of the decade. IonQ uses trapped ions, individual atoms suspended in electromagnetic fields. These qubits have naturally long coherence times, though scaling to large numbers is challenging. Atom computing employs neutral atoms arranged in optical lattices, demonstrating systems with over 1,000 qubits. Each approach has advantages. Superconducting qubits are fast, trapped ions are precise, neutral atoms scale well. Topological qubits are stable. The race is not to see which technology wins, but which combination of technologies can first cross the threshold to quantum advantage, the point where quantum computers can solve problems no classical computer can match. As of 2025, we have achieved quantum supremacy on carefully chosen problems. Google demonstrated this with random circuit sampling. But we have not yet achieved quantum advantage on problems that matter to industry and science. The topological approach offers a particular promise. Once you build large enough arrays of topological qubits, the error rates might be so low that you can skip layers of error correction entirely. You might calculate directly on the hardware-protected qubits. If Microsoft's roadmap holds, they could build a fault-tolerant quantum computer in years, not decades. Imagine for a moment that they succeed. That by 2035, 1 million topological qubits are performing calculations no classical computer could verify. What changes? Pharmaceutical development collapses from decades to months. The drug that might have cured your grandmother's disease but wasn't discovered in time, it exists now, designed by quantum simulation of molecular interactions. Energy storage transforms. Batteries with 10 times the capacity of lithium-ion, manufactured from abundant materials. Solar cells approaching theoretical efficiency limits. Nitrogen fixation, the process that converts atmospheric nitrogen into fertilizer, currently consumes 3% of the world's energy and depends on a century-old industrial process. Quantum computers could design catalysts that do this at room temperature, the way bacteria do. Food security for billions. Logistics optimization. Every delivery truck finding the optimal route not through heuristics, but through exact calculation. Every flight path adjusted in real time. Waste reduced by orders of magnitude. But perhaps the deepest transformation is epistemological. For 4 billion years, life on Earth has been classical. Neural networks, including our brains, process information according to classical rules. With quantum computers, we will, for the first time, have partners in thought that process information according to quantum rules. Entities that can explore questions we cannot even properly formulate. The relationship won't be human versus machine. It will be human and machine, each compensating for the other's blindnesses. Classical intuition guided by quantum calculation. Quantum results interpreted by classical understanding. We will become, in a sense, hybrid thinkers. Part classical, part quantum. Biological minds augmented by topological mathematics. In the spring of 2025, in a laboratory in Santa Barbara, 8 topological qubits performed their first measurements. 8 knots in the fabric of quantum mechanics, encoding information in topology. They are just the beginning. A proof that the impossible is possible. That information can be stored in geometry itself, in patterns the universe cannot accidentally erase. The quantum computers of today fail because they fight against nature. They try to isolate themselves from a universe determined to intrude. They build walls against entropy and watch those walls crumble. Topological qubits do something more elegant. They don't fight nature. They use it. They encode information in structures that nature itself protects, in conservation laws, in topological invariance, in the mathematics that the universe must obey. In a way, they have discovered what the universe has known all along. that the most permanent information is written not in matter, but in the shape of space itself. For the first time, we have built something the universe cannot break. Something that stores its knowledge in the geometry of existence, and that changes everything. This is Cosmic Canvas, where we explore not just what we can build, but what the universe itself protects. Until next time, remember that permanence is not found in power, but in the geometry of truth.